Okay, so as Professor Shannon said, thank you very much for sticking around to the end of this tutorial. My name is Shane Kanaile, and I am located at the University of Illinois, and we have developed, as part of the Moose framework, CRANE, which stands poorly for Chemical Reaction Network. So this talk is going to just be an overview of what CRANE can currently do, and I'm not going to show you the code, I'm just going to show you how you can use it and show you examples of use, just so you don't get scared away. Okay, so to start things off, CRANE is an open source software dedicated to modeling the time evolution of coupled rate equations. And something I'll get into in a couple slides, we've leveraged the action system, which is developed in Moose, to accept an arbitrary number of human-readable reaction equations. And originally, CRANE was developed with two different use cases in mind. As a global model, comparable to ZD-Plaskin, if you're familiar with that, or as part of other Moose applications, it can be used in a spatial model as well, so from 1D to 3D. Yeah?
Do we cover the action?
No, I'll talk about it a little bit here. But yeah, we didn't talk about it in the tutorial. Okay, so the mathematical kernel of the software is simply a system of ODE equations. So something we should all be familiar with, I'll use the cursor here. Equation 2 is just an arbitrary reaction between two species and producing a third species, C. So just using chemical kinetics, the source term or sink term that CRANE sets up for you to solve. So the focus of CRANE, though, is not just developing these kernels, because those kernels are pretty simple to write. The focus is the action. So Moose, built into Moose, is an action system, and what this does is you can use it to automatically add pieces of physics or materials or variables to your input file. So there's a couple kernels to each variable, but you can imagine if you have a 20 variable system, all of them having drift diffusion components and all of them having reactions between them, the input file can get very complicated very quickly. So CRANE was built to focus on the reactions between those variables. So instead of having to add, in this case, 6 different kernels, you can just write the reaction equation, a subblock called scalar network. CRANE comes built in with two subblocks, network for spatial problems. So if you have a plasma transport problem, you can use network. A couple CRANE and use network. Or if you're using it as a standalone, you can use scalar network for a global problem.
So in this case, are these species then variables?
Yes, these are the nonlinear variables in the system. Yeah. Yes?
So is this similar to the reaction ones in COMSOL where you provide the co-reaction equations?
Yes. The equations out in the input file.
And can I import data from the LXCAT database, like after downloading them?
Yeah, I'll talk about that in a minute. So there's no direct coupling for using cross sections, but we are using Boltzig Plus data here. So you can run Boltzig Plus and use that data to calculate rate coefficients. Yeah. So I will get into that in a minute. Okay, so let's dive into that reaction network that I showed you previously. So as I said earlier, the action automatically counts the stoichiometric coefficients, the reactants, and the source and sink term for electrons, argon neutrals, and argon ions. In the scalar case, rate coefficients, are included as auxiliary variables, which can be calculated at the beginning of each time step. You can also set it to be calculated at the end of each time step if you need to. So there's a few different options in the most basic case for using this action. So first is speeding for in the system. So you'll, when I start showing you full input files, these will be in the variables block that you've seen earlier in the tutorial. And just based on how these chemical kinetics equations are set up, all reactants must be either nonlinear or auxiliary variables, because those are into some arbitrary sink term. You can put anything you want on the right side. If it's not a variable, it will just be ignored. The most important part of this is obviously the reactions list. So this lists all the reactions that you want to be solved with rate coefficients separated by a colon character. So in this case, we have yields 2 electrons and argon ions, so it's just electron impact ionization. And the action will automatically parse that into reactants products and add the necessary kernels from that. In this case, this is what you were asking about earlier. If you say EEDF instead of giving like some kind of constant rate coefficient here, that tells I have run Bolsig plus prior to writing this input file, and it'll look for a rate coefficient tabulated as a function of electron temperature or electric field, whatever you tabulated it as in Bolsig plus. And it will automatically calculate the rate coefficient from that file. Add an energy term right after the rate coefficient by enclosing it in brackets. So if you put left bracket -10 right bracket, it'll automatically add an energy term of 10 eV to the electrons. Or if T gas, if the gas temperature is also included, it'll also add that term, EEDF rate coefficient. If you're using that, you need to list a file location. So this is saying that it's looking, when it's trying to calculate an electron energy distribution function rate coefficient, it's looking in this file for those tabulated data. So in this case, it's going to look for a data file named, since we say rate coefficients, it's going to be looking in the rate coefficients directory. I'll give an example of this later if that seems confusing.
Can I ask a question about the types of?
Yeah.
So for your reactions, you've got mainly electron impact reactions.
Yeah.
For example, can I have spontaneous de-excitation run? So if I'm also tracking as opposed to just electrons, I can track their production through one reaction that's electron impact, and also track another reaction which is going to be the spontaneous de-excitation of that excited state.
Yeah, if you can put it into some kind of reaction form like this, like reactants, yields, products, and you have a rate coefficient for it, then yes.
Okay.
Yeah. It's,
Provides results in either Boltzmann, if they're solving the Boltzmann equations or the Maxwellian, it has options for both.
yeah.
But let's say I want to use it for Rubinstein, and then let's say I have an app or I have a method of code that spits out reaction data for a Rubinstein electron distribution function. How am I going to import that?
Yeah, so all energy or electric field or what have you. So as long as you can put it into a form like that, then yeah, this Crane just cares that it has some kind of rate coefficient to provide. It doesn't care about what the distribution function looks like. Yeah, so that should be fine. Whether or not that works when you start putting it into, like, coupling it into fluid codes, I can't say.
So there must be a different format for that.
Yeah. Okay, so on the right-hand side of that colon, there are 3 different rate coefficient formats that are accepted. Constant, which you saw earlier, that's simply just a constant value. EEDF, which you also saw, so this is going to look for tabulated rate coefficients. Or you can also have the option of including an explicitly written equation. So if you have a rate coefficient that's in Arrhenius form, you can write that explicitly. Variable or constant. I will show an example later, but if it's a constant or variable, you need to give equation variables. Like if T gas was a variable, a nonlinear variable in the system, there's another action option equation variables. So you'd list that under there, and it would know to look for a nonlinear variable for that. Yeah. Okay, and as I said, Boltzmann Python equivalent called Bolos, which I have also used, and they get pretty much the same results. Or as you were saying, if you have your own in-house software, as long as you can get rate coefficients out of it, that's fine. Okay, and as I was saying earlier, if an EEDF rate coefficient is included, Crane will look for files of tabulated rate coefficients. So for example, it'll be under Crane problems, whatever file you called it, rate coefficients file. If no file is specified, it'll search directly inside the problems directory. So you can just put them directly in there if you have a simple simulation to run. And as I said earlier, the files must be named currently after the reaction they are applied to. So it's going to look for a file named after that reaction. In the future, I'd like to include an option for have this convoluted file name. You can just tell it what file name to look for or what reaction to look for. Okay, so the units of rate coefficients are entirely up to the user. Again, Crane is just solving an ODE system. It doesn't necessarily need to be physical units. All you need to make sure of is that the nonlinear variables and rate coefficients have consistent units. So if your species densities are, so when I say that the electron energy distribution function rate coefficients are tabulated as a function of something, that function, the variable that it's a function of needs to be, well, Boltzig Plus treats it as electron temperature or electric field. In principle, you can tabulate it as a function of anything as long as that reduced electric field, electron temperature, or whatever variable you're using is a variable in the system. It can be either nonlinear. So the suite of kernels available in Crane, yes? Yeah, I have installation instructions in a couple slides, but I guess, or one slide. You can clone this from the Laboratory of Computational Plasma Physics GitHub, Git repository. It's in there. So you are free to do that. And in fact, I will ask you to do that if you are comfortable with doing so. Three-body reactions. So this is just a simple table showing the three different kernels. So in these equations, in the center column here, nu is the stoichiometric coefficient, k is the rate constant, or rate coefficient, and n sub a, b, or c is just the species densities. And it will automatically read reaction written in that form. Okay. So with that said, I'm going to stop. The next section will go over some example problems to give you an idea of how to use Crane. And if you download it and install it, you'll be able to run those input files yourself. Okay, that was easy.
So if I had something that was I'm going back to the photoionization
Yeah.
thing. So if I was tracking photon flux as a track variable,
Okay.
then I could put that in just like I would electron temperature, gas temperature, or anything else, and calculate a rate coefficient from that, right? I mean, it doesn't have to be a temperature. It can be a you know, I guess it could be a density. Okay.
Yeah.
So maybe that is a.
Yeah, I mean,
I'm not sure what the best way is to implement it.
yeah, but as long as you can write, and whatever system you're talking about is a system of ODEs, then it can be solved. Yes. Mm-hmm.
I'm getting an error when I'm running make.
Okay.
So if you can.
Yeah. Mhm.
The density is most likely constant, doesn't change.
Yeah.
So you have option to set that as constant, so you don't need to sort the density.
Yeah, you can set, if you set it as an auxiliary variable, that doesn't change, so it's just a nonlinear variable, so it won't be included in the nonlinear solve. So yeah, you can. One of the examples shows that actually. So as you can see, if you look through the Crane files that you've just installed, input files, and this is true of most Moose applications in general, input files are typically stored in the application's problems directory. So if you look under Crane/problems, you'll see a few input files in there that we'll be running next. And as you've seen multiple times in the opt, you have the input file flag -I, and then you input your file name. Okay, so with that said, here we are going to start the simulation examples. Again, these are in the problems directory for you to follow along if you'd like. So the following examples focus on solving reaction networks both within plasma discharges and in more general ODE system cases. So the first one is a predator-prey problem, so just the Lotka-Volterra equations, the non-stiff ordinary differential equations. And the next three examples are more specifically plasma discharge relevant examples. So we have argon chemistry, nitrogen chemistry, and a final hands-on example for you to use if you want. It's a simple two-reaction test case. Did you have a question? Okay. So let's start with example one. This is listed as example1.i in your problems directory if you'd like to look through it. So this problem is simple reactions in this case, consumption and production rates of each species. So in this problem, x and y are the nonlinear variables that will be solved by Crane, and a, b, c, and d here are the rate coefficients. So in order to be solved by Crane, the problem must be cast into a system of reactions. So these problems don't necessarily list reactions in the traditional sense, but this problem applies the equivalent ODE system here. X plus y producing y, so this essentially just destroys x at a rate of b, which is this problem here, and the other two are shown here. And you can see here there's a factor z. That's just showing that that's an arbitrary sinc term. Z is not a variable in the system, so it's not tracked. It's just saying that y is being destroyed here with a rate of c, so it's going into nothing. So the problem statement here is we're using arbitrary units, so t time is going from 0 to 50, is 1, d is 1. Yes?
Give an example of x being 2x.
It's just a mathematical form. I'm just turning this term here into a.
What's that?
It's a doubling rate for population.
Oh.
Yeah.
Yeah, okay.
Yeah. Okay, so as I said, this problem is located in the problems directory. It's labeled example 1. To run, do as we've done throughout example 1. So I can show that to you right here. And again, you are free to run this yourself. See problems. I have more examples than you because I did not upload everything. But you can see here, example1.i. So we're going to run that. It outputs all scalar variables to the terminal. You can optionally turn that off, especially if you have massive reaction networks that might be annoying. But you can see here there's the time, the rate coefficients, 1, 2, 3, and 4. So this is A, B, C, and D, and the populations, X and Y. Yeah.
Can you please repeat the GitHub website address where we can download that PDF?
It's in the there's only one file in there, so you can look in there. Yeah. Oh, I already have that open. That's why I closed it. Okay, so just to look at that input file really quick on kernels that you're familiar with from the tutorial, we're using scalar variables and scalar kernels. And what this means is that they don't exist on the mesh. They're just a scalar value. However, to run Moose, we need a dummy mesh, so we just input a one-dimensional mesh with one element, and that allows it to run. It has no effect on the problem because the variables don't exist on that mesh. Scalar problem, and first order, and we're giving it an initial condition of 1 here. And the same for y. For Crane to work, it adds all of the reaction kernels through the action, but you need to add the time derivatives yourself currently. Eventually, I'll add an action that does that automatically. But for now, we have 2 time derivatives. And again, since these are scalar problems, we're using class action. So you can see here, species x and y, reaction coefficient format rate. This is just saying it's using a rate form that's not necessary for this problem. It's there just as an example. And we have the reactions list. So these are 4 reactions that you saw in the slides with the rate coefficients separated by a colon. Do you have any questions? Okay, like in energy? Yeah, in this case, these problems do not have energy, but you would do it like this. But if there's no energy, in this case, you would also need to say energy equals, and you'd give it whatever variable you're using. If you don't have that, it will read this energy term, but it won't apply it. The rest are things you've seen before. This is a transient problem, starting at 0, ending at time 50. And we've included a preconditioning block, which you saw before lunch today. Okay, so also included in your problems directory, there's a Python script associated with each of these functions, except for the second example. So if we look in here, we have example1plot.python.py. So if we run that, scalar variables here, I find it very convenient to output to CSV format because it's just variables as a function of time. You can also export it to Exodus as we have before, but it's very convenient to plot CSV files directly like this. Okay, does anyone have any questions about this example? If not, we can move on. Do you have any questions? No? Okay. So if you successfully ran that example, this is the output you would see as I just showed you. It's simply the classic predator-prey problem, so species. Okay. Yeah.
Do we have to specify what kind of reactions they are like? Are they elastic or ionization or de-excitation?
Again, I'll get into this later in a different example. For ionization and excitation, you can just give it a rate coefficient and give it an energy. It doesn't care. For elastic, you write in brackets elastic, and it will calculate. There's a simple form I can show you.
So it just calculates like an average
Yeah.
most probable energy loss for.
Yeah, based on the masses of the target, of the electron target, yeah. I don't need to show.
It's not like you're updating the distribution, so you're not doing something like
Yeah,
a background distribution function you're sticking with, right? That's one of your very.
yeah.
Okay.
Yeah, we don't have any velocity distributions or energy distributions here, so we can't actually calculate the real energy, elastic energy change, I guess. It's just an average value. Okay, if you are all ready, I can move on to the next example. Model, and if you recall from the slide a few slides ago, this is meant to show Crane solving both stiff and non-stiff ordinary differential equations. So this model shows a simplified 3-level hydrogen system, and it's generalized into 3 mass fractions with 6 transition for ground state hydrogen, excited hydrogen, and ionized hydrogen, and there's 6 transition frequencies between those 3 states. So this system corresponds in physical terms to electron excitation, de-excitation, or electron ionization of the excited state, and direct ionization of the ground state. And the reverse reactions of all 3 of those. In this problem, yeah. Yeah. So this system, this was taken from the thesis I cited at the bottom of this page if you'd like to look it up yourself. But this system may be cast into a system of 3 reactions that I showed previously, which itself may be formed into an ODE system of 6 transition. Those are essentially the rate coefficients in this problem. And the non-stiff case is shown on the right. So the frequencies are much closer together, so the problem is very non-stiff.
Stiff and non-stiff in the sense more accurate and less accurate.
No, those are like mathematical terms. You can kind of see what it means by stiff and non-stiff.
Very fast variations. So the integrator has to be able to respond to the fast variation as well.
Yeah. So for example, this transition happens at time, something on the order of 10 to the 10 frequent transitions per second.
27 gigahertz.
Yeah, and then they're all essentially the same. They're very close together. Okay, so again, this problem is in the problems directory for you to follow along with. It is named example 2. You can run it the same way we've run previously. In this case, I won't plot it. At least I won't plot it through the Python script because this required running 5 different starting points or initial conditions for each in both the stiff and non-stiff case. Okay. So on the left here, we can see the stiff trajectories. So the labels T1 through T5 are the initial conditions in phase space. So we have, I'll use the cursor here, hydrogen, excited hydrogen, and ionized hydrogen, or F1, F2, and F3 in the source code. And on the right, we have the non-stiff trajectories. So you can actually kind of see what they mean by stiff and non-stiff to answer your question.
I think I'm trying to understand the plot because this is the first time I'm looking at a phase space plot.
0 to 1, so 0 to 100%. You can think of it like that. Like that. So all of these initial conditions, you'll notice sum to 1 because there's only 3 mass fractions in our system. So each one, all of these mass fractions sum to 1. So we have only 100% in the system. Does that make sense? Yeah. That means if you want to look at the input file. Yeah, to plot that, I ran it with each case with 5 different initial conditions and saved the output files to different CSV files. Okay, so here is our variable here, or variable system here. Again, they're scalar variables following the paper respectively. And you can see the initial conditions here. So this is in the presentation where it lists T1 through T5. Those are the initial conditions for each species. Does that make sense? Okay. And this is the reaction network again. These? Yeah. Those were just tabulated. They were constants. I just took these are not meant to represent a truly physical system. They're just meant to exemplify a very stiff and very non-stiff problem. Yeah.
But in reality, they can be extracted from.
Okay. So I'll, with that said, I'll move on to a more physically relevant example, which is what you were asking about. So in this case, this follows if you are familiar with ZD Plaskin, this follows ZD Plaskin example 2. It's a microcathode argon discharge, doubly ionized argon, excited argon, and electrons. So this example is meant to demonstrate the capability of Crane to use both rate coefficients and other variables, other different variables in the system that aren't necessarily species densities. So all species are nonlinear variables, and the reduced electric field is electron impact rate coefficients, of which there are several in this system, were calculated externally by Bolsig Plus. And they are tabulated here as a function of reduced electric field. And I can show that to you in the problems directory if you'd like. So in this problem, we have our initial conditions: electron, ionized argon, and excited argon are all starting at 10 to the 6 number, and doubly ionized argon starting at some small value. It doesn't matter. These parameters, recall this is 0D, but we have dimensional parameters used in the calculation of the reduced electric field. All of this is taken directly from the ZD Plaskin example. Cover a couple of the different pieces that we've included in this file that are different from the action you've shown, or I've shown you, just to cover some of the other capabilities. Yeah?
Instead of this code, can you show the actual file? Is it possible to use the actual file? What is code is there? That way it might be easier for us.
The input file? I can open it for you here. Okay, so again, we have our dummy mesh. This variable does not need to exist. I was playing around with this earlier. Argon ions, neutral argon, excited argon, and doubly ionized argon. You can call them whatever you want. I named them explicitly because that's easier for me. This kernel does not need to exist. Okay, and then, and here is the action. Let me open this a little more. Is that still on the screen?
Yeah.
Okay. Good. Okay, so here we again list our nonlinear for you. So if you look in example 3, you'll see 4 data files which have tabulated rate coefficients. Yeah, this, again, I was playing around with it. Scaling will scale you might have convergence issues. And I was playing around with scaling parameters there. Okay, does anyone have any questions about this? I'm using the Moose template in Atom. So it's just, I do not recall because Casey did it for me.
So if you actually go to the mooseframework.org webpage, and if you go from there to help, once you click on developer tools, there's a entry that says set up Atom editor for Moose. See that?
Yes.
And if you click on that,
Not found. It says not found.
it seems to have been broken. So I will email the appropriate people at INL to get Dr. maybe if you're interested.
Okay.
Because it's essentially a combination of several packages that you can install in Atom that give you that ability. And almost all of them were developed by one staff scientist at INL that uses Atom religiously as his editor. So
There are some other links also which were broken.
for Moose. And unfortunately, there have been a few quirks with that transition. So I apologize for that.
Yeah.
So the last 3 reactions there, they go to W. What does that W represent?
Yeah, that's just, so it's just, E is just, electrons are just disappearing with a rate shown here. So this could be anything. Yeah. Yes, yeah. Again, this is following a ZD Plaskin example. So it's just meant to represent. I'm going to cover a couple of the different factors here because there's a few more options that you can see in the action. First, you can see the EEDF rate coefficients. So if I go into the crane directory here. And we go into example 3, you can see the 4 rate coefficient files. So it's rate coefficients on the y-axis tabulated as a function of reduced electric field. In this case, the reduced electric field is calculated in physical units, so it's volts, volt meter squared.
So where does that voltmeter square input come from?
Bolsig plus. Right now. Okay, so we also have functional rate coefficients here. So you can see these terms enclosed in curly brackets. These are explicitly written equations that will be calculated every time step as needed. So in this case, we have a rate coefficient that is a function of electron temperature. The electron temperature, which I will show to the rate coefficient solution here. And also, T gas is given as a constant here. So we can see equation constants, and T gas is assigned a value of 300. So it's room temperature, 300 Kelvin. Yes? You just need to make sure that that's either nonlinear or auxiliary variable in your input file. Right. This is the sampling variable, essentially. Actually, this is a deprecated version. It still works, but we have variable. So in that way, whatever variable you're sampling with, whatever you tabulated those rate coefficients as a function of, it.
Tabulated set of data.
Mhm.
If my sampling variable is a track variable in whatever code I'm running, I'm assuming it just linear interpolates between the two, or how's it?
It's a spline interpolation right now. If I remember correctly. I'm not sure. But right now it's a spline interpolation. Yeah. So yeah, because if you see here, you might not have a reduced field value exactly here. It might be in between these two, and it will interpolate those values. Okay. So here we're giving it an initial condition, but this is actually being calculated, which I will show you in a moment, with a function. So every time step is being calculated, and that value is being used to sample the rate coefficients. The other 3 variables, mobility, electron temperature, and current, are also calculated with a class called parsed auxiliary scalar. So all this means is instead of giving it some kind of constant value or writing explicitly an equation in a kernel like you've seen before, we're passing it a function here. So it'll calculate that function. Again, all of these functions. And we also have the parsed auxiliary scalar for current, mobility and electron temperature are taken from Bolsig plus as well. So if you look in that example 3 file, you also see electron mobility and electron temperature. So those are all tabulated as a function of reduced field. I could have done this electric field tabulated with electron temperature, if that makes sense. It depends entirely on your preference. Okay.
We have one file, so is it you able to use one file for either subject?
Right now, you can't just flip it like that. So you need to include both if you want to flip it. So I've included an adaptive time step, which we talked about earlier, I believe yesterday. So what this is saying is it's starting with a time step of 10 to the negative 10 seconds. And every time step is increasing that value by a factor. This just means that by the end of the simulation, I'll be running with a much larger time step than 10 to the 10. So it makes your simulation time faster in general. So I can, that's the factor. If it fails a convergence, it'll cut back the time step by that factor. So we can run that problem. Diluted because there's so many of them. It outputs all of the rate constants. Those are, Crane calculates all of the rate constants that we've input as auxiliary variables themselves. So you can also, those are also exported to the CSV file if you like to see how the rate coefficients evolve over time. But there we go. There we go. So you can see at the start, these are our initial conditions, and you can just see the evolution over time of these. Okay, can you all hear me? The clip-on microphone died. You might get a slightly different result if your input initial conditions are different. I believe they're the same as the ones I ran, but shown here is the same results I just showed, except they're plotted against the ZD Plaskin example. So you can. Do you have any questions? Yeah, it's in. It's again a 0D plasma chemistry solver. So it's similar to Crane in that you can explicitly write the equations in a human readable format. The benefit here is just that Crane is a part of the Moose framework, which means it can be scaled up to dimensional problems.
So now the CSV file or the plot file that is being exported, does it only record or only store the species concentrations value?
No, it'll store all scalar values, including auxiliary scalar values. So I can show you the output folder if you want. If you run it yourself, you'll also see this. Here we go. Yeah. So variables, rate coefficients, all of those are tabulated in the output file.
So
Yeah.
That's what I wanted to know if you have the temperature of the one.
Yeah.
But when you are plotting it with Python, it's only showing the species variable. It's because of some folks.
I wrote those Python files myself just so you could view the results alongside me. You can open that Python file and you'll see what it's doing. It's just loading this with NumPy CSV read or something. And I yeah, yeah.
What was the limit state that Python, to run that Python script to?
Oh, it's just Python. I can show you. Easier to write than say. Yeah. Yeah, that's not a Mac thing. That's just how you run Python. Are there any questions about this example? So the next example is a bit more complicated. This includes 34 reactions between 11 species. And this is, again, one of the ZD Plaskin examples, which is convenient because it's easy to compare to. So in this example, I'm going to show a couple different things. In this case, where electrons are not going to be a nonlinear species in this system. Instead, you can assume that this is electron density, so we're reading that in from a data file. And the reduced electric field, again, is calculated based on electron mobility, gas density, and the physical domain of whatever fake experiment we pulled this data from. Okay, so initially we just have nitrogen at atmospheric pressure and all other densities are 0. Our gas temperature here is 300 Kelvin, so it's just an atmospheric in the rate coefficient calculations, which I'll show you in the input file in a moment. And if you want to follow along, this is example 4.I, alongside all the other examples I've shown you. Okay, I think it might be better if I just show you the input file. So here is example 4. So here are all of the variables that we're including in the system. I used very high precision for this density. That is just calculated from atmosphere. 2A1 and 2C, those denote different excited nitrogen species.
So I didn't understand,
Yeah.
how did you input that atmospheric pressure? Where was the,
This?
no, yeah.
I mean, that's, what do you mean, how did I input it?
No, you just said atmospheric pressure, right? That's,
P equals NKT. So this is density calculated from that.
oh,
Yeah, so P is atmospheric pressure, 760 torr.
yeah.
Have all the time derivatives for all those variables. And here is the reaction network. So there are 34 reactions between all of those species. Again, we have electron energy distribution functions calculated from Boltzmann Plus as before. And they are again being calculated from tabulated against the reduced electric field. And this here in a couple of these rate coefficients, you'll see that T effective value that I showed in the slide. This is an auxiliary variable, so it's listed in equation variable EFF. Okay, so then we have our auxiliary variables, including this, in this case, electron temperature or electron density. So recall I said we're reading electron density from an external file. It's not being calculated as a nonlinear variable. So here we list electrons as an auxiliary species with that command here. So this means that electron density is not going to be, yeah.
So you have the electron density specified in both species and ox species?
Yeah.
Ox species definition override the species definition?
Yes. Yeah.
So, okay, so then why would you also have it in that list in species?
Because originally it did not override it. It needed to be included in species originally. So this is an old input file. Currently, I believe it should be able to add it. You don't need to have it in the species declaration. Yeah. So it's just, that just means it's reading values from an external file to a scalar variable. So this is how we're reading both electron temperature and electron density. So if you look in the folder example 4, which is again in the problems directory which you've been working in, you can see all of these rate coefficient files along with electron density and electron temperature. And you can see here there's another option called use time, and time step you're at, it will read that value from the time variable. Does that make sense? Okay.
So this is the electron density is the one that you said that from the experimental electron density.
Both temperature and density of electrons are read, but yes, they're experimental values.
And they are here in terms of what one? Like what's on the
They're tabulated as a function of time. Yeah. So shown here is a different time stepper. The time steps that are in that input file, it's using those specific times. So we're not setting a time step, it's just calculating everything as at every single time listed in those files. So if I open one of those files here, oh, that's the wrong one. So the x-axis here is the time variable, so it's just going to, the delta t is just, or it's every time step is going to be these values of time, if that makes sense. So it's reading the delta. So you can feel free to run that yourself. I will run it here. And that ran pretty quickly. If I plotted that, you would get this. This is only a small sample. Again, there are 14 species. I'm not going to plot one species. And this again favors almost identically to ZD Plaskin. Does anyone have any questions about this example? I'm sorry for the people who just walked in and are confused about this plot.
It
sums up the whole 2-day workshop. So interesting.
Okay. Cool. Pre-made examples using Crane. I already made those input files, and you can run them yourself. But the point of this is hopefully so you guys will run Crane yourself. So this next example is hands-on. So you can try writing the input file yourself. I've included a try finishing up the next example by yourself, and I'll give everyone about 10 minutes to do that. There's not much. So this example is simply 2 reactions between 3 species. So we have argon, argon ions, and electrons. So all we have is electron impact ionization and some kind of deionization term at a constant value. So you can create a reduced electric field auxiliary variable and just give it an initial condition of 50 Townsend and leave it like that. You don't have to add a function to it. So with these parameters, this becomes a system of 3 coupled ordinary differential equations with constant rate coefficients. The reduced electric field, as I said, is an auxiliary variable. So here are your 2 equations, and you can write those in the chemical reactions block as you've seen in the previous 4 input files. So I will give you some. The only missing pieces are a couple more variables. Electrons are included right now, but you'll need to include the argon and argon ions. And you'll need to add the scalar kernels for ODE time derivative and fill in the 2 reactions.
Just one question.
Yeah.
Here in Crane, whenever there is 2E, I have seen that you always show E plus.
Yes. That is just a parsing thing that I don't know how to get around. So always write it as E plus E. Yeah. And again, you can look for examples of syntax at the previous input files. And if you need help, I will come around and help you. Okay, everyone, it looks like at least half of you have gotten to the point of running this and getting the right result. In the interest of time, I'm going to show you the correct input file, which most of you have gotten already, and then close up this talk. Okay, so for this problem, if I'll go back to the initial conditions, two scalar variables, argon and argon ions, two time derivatives for those variables, and the reactions. So I can show that to you right now. Okay, we don't need scaling. So here in the variables block, you should have something that looks like this. When we added two time derivatives chemical reaction network, we added three species, electrons, argon, and argon ions, and added the two reactions between those species. Okay? Everything else should already be written in the input file for you. If not, something horrible has gone wrong. Yes?
What is the plus plus doing in the second reaction? Oh, it's argon plus.
Yeah.
In addition.
Yes. So anything that doesn't have a space is red. Atom does not recognize that as a variable term. Yeah. Yeah. Okay. And again, if you run that problem, you get this result. It's just two reactions at two constant coefficient reactions, so it just reaches a simple steady state between the two, between the three variables. Does that make sense to everyone? Yeah, and I can run that. And I ran into an issue. Oh, I see. I was playing around with different solvers. There we go. Okay, so does anyone have any questions about that example? After this, if you still weren't able to get it working, I can come around and help you with it. Or I will also put the completed input file on the repository right after this so everyone has access to it. Okay, so with that said, I'd just like to summarize that Crane is a fully open source software. So I encourage all of you to download it in collaboration with anyone who wants to use it. So once again, this is stored on the lcpp-org/Crane repository. So it is freely available for you to use. And if you'd like to contribute, you can fork this repository as you would any other GitHub repository that you're trying to contribute to get projects like that. There's lots of tutorials on it, and I can also help you after this. So for questions, concerns, or comments, you can contact me or look at my own personal GitHub repository. And also for Moose in general, there is a Google group for Moose that has been very helpful to me. Okay, so with that said, if there are not any more questions, I think we can take a break. Corey will cover that at the end of his Aptos talk. Yes. Are there any other questions? Yes. Okay, I'll finish this up and come help you.
So you want to run a break before we get to Corey? Or?
It's up to you. It depends how much time we have.